The future of energy has always been sold to us as a simple equation. More solar panels, more wind turbines, more clean electricity. But there's one problem that never goes away. No matter how advanced the panels become, no matter how efficient the technology gets. Energy storage. Because electricity is only useful when you can store it, and then use it when the sun is gone and the wind is still. For decades, the world has depended on one dominant solution: chemical batteries, mostly lithium-ion systems. They power our homes, our phones, our electric cars, and even entire solar farms. But behind the convenience lies a quiet reality that most people never think about. These batteries are expensive, they degrade over time, and eventually, they must be replaced. Now, according to multiple publicly available energy industry reports, battery storage can represent a significant portion of the total cost of a solar installation. In some residential systems, it can be the single most expensive component. And even after you pay that cost, the clock starts ticking immediately, because every charge cycle slowly wears the system down. Every year reduces capacity. Every replacement cycle adds new expense. So the question engineers and researchers have been asking for decades is simple, but extremely difficult to solve. Is there a way to store energy without chemicals, without degradation, without constantly replacing expensive components every few years? And that is where a very old concept has suddenly returned into modern scientific discussion: a flywheel. Now, at first glance, a flywheel sounds almost outdated, something from old mechanical engines, industrial machines, or historical engineering textbooks. But in reality, the concept is surprisingly simple and extremely powerful. Instead of storing energy in chemicals, a flywheel stores energy in motion. A rotating mass spins at extremely high speed. When energy is supplied, like electricity from solar panels, it is used to accelerate the rotation. And when energy is needed, that motion is slowed down, converting kinetic energy back into usable electricity. No chemical reactions, no degradation in the same way as batteries, just physics. And that simplicity is exactly why researchers never fully ignored it. But there was always a problem. Early flywheel systems were limited by friction. They were heavy, they were unsafe at high speeds, and they lost energy too quickly to compete with batteries for everyday use. So for years, the technology stayed mostly in industrial or niche applications. But recently, something started to change. Advances in material science, magnetic bearing systems, vacuum-sealed chambers, and precision engineering. All of these developments have reopened the conversation around whether flywheel systems could finally become practical for modern energy storage, especially in renewable systems like solar. And this is where the claims start getting attention. Because some discussions in engineering circles suggest that, under the right conditions, flywheel-based storage systems could reduce long-term energy storage costs significantly compared to traditional battery systems. Some even describe potential cost reductions that approach dramatic figures when life cycle, replacement, and maintenance costs are considered over time. But this is where we need to slow down and separate engineering reality from public interpretation. Because while flywheel systems do have real advantages in specific use cases, the idea of replacing batteries completely is far more complex than it sounds. And understanding that complexity is essential before we can answer the real question behind this entire discussion. Is this truly the beginning of a new era in solar storage? Or just another misunderstood technology being pushed into the spotlight? At this point, we need to go deeper, because to understand whether a flywheel system can actually change the economics of solar energy storage, we first need to understand how today's battery systems dominate the market and why they became the standard in the first place. And more importantly, we need to understand what they do better than almost anything else currently available. The reason lithium-ion batteries became the global standard is not because they are perfect, but because they solved the problem better than everything else available at the time. When renewable energy started expanding rapidly in the early 2000s and 2010s, the world needed a storage system that was compact, efficient, and scalable. Lithium-ion technology delivered exactly that. It offered high energy density, meaning a large amount of energy could be stored in a relatively small physical space. It also allowed for fast charge and discharge cycles, which made it ideal not only for phones and laptops, but eventually for electric vehicles and home solar systems. According to widely published energy research data, lithium-ion batteries quickly became the backbone of modern energy storage infrastructure, because they were simply more practical than older alternatives like lead-acid or nickel-based systems. But practicality does not mean perfection, because as adoption increased, so did the limitations. One of the most widely documented issues is degradation over time. Every charge and discharge cycle causes microscopic changes inside the battery's chemical structure. Over thousands of cycles, this leads to reduced capacity and performance decline. In simple terms, the battery slowly becomes weaker, even if it is used correctly. Another challenge is thermal sensitivity. Batteries require careful temperature management systems to prevent overheating, which adds additional complexity and cost to large installations. And then there is the supply chain factor. Lithium, cobalt, and nickel are not unlimited resources. Their extraction involves environmental impact, geopolitical concentration, and fluctuating market prices that directly affect the cost of energy storage systems worldwide. So while lithium-ion batteries are currently the dominant solution, they are not without long-term concerns, especially when scaled to global renewable energy demands. And this is exactly why alternative technologies continue to be researched. Not because batteries have failed, but because the world is looking for something that can last longer, cost less over time, and ideally reduce dependency on rare materials. Which brings us back to the flywheel. Because unlike batteries, a flywheel does not store energy chemically. It stores energy mechanically, and that difference changes everything about how it behaves over time. In a modern flywheel system, energy is used to spin a rotor inside a sealed chamber. This rotor is often supported by magnetic bearings, which significantly reduce physical contact and friction. Many advanced designs also operate in a vacuum environment, which minimizes air resistance. The result is a system that can spin at extremely high speeds while losing very little energy over time. In controlled industrial applications, flywheel systems are already used for short-term energy stabilization. They help smooth out fluctuations in power grids, provide backup power for critical infrastructure, and support high-performance systems where rapid energy discharge is needed. In these environments, flywheels perform extremely well. They respond quickly, they handle high cycle rates, and they do not suffer from chemical degradation in the same way batteries do. But there is a key difference between industrial use and home energy storage. Industrial systems are typically designed for short bursts, not long-duration storage. And this is where the debate becomes more complex. Because when people hear claims like 90% cheaper energy storage, they are usually hearing a simplified interpretation of a much more complicated engineering comparison. Cost in energy systems is not just about the device itself. It includes installation, maintenance, efficiency losses, lifespan, replacement cycles, and infrastructure integration. A battery might have a high upfront cost, but it is easy to deploy in homes. A flywheel might last longer in theory, but requires precision engineering, safety containment, and mechanical balancing systems that are far more complex than simply installing battery packs. So when engineers discuss cost reduction, they are often referring to long-term lifecycle economics rather than simple purchase price. And that distinction is extremely important. Because while flywheels may reduce replacement frequency and material dependency, they introduce their own engineering challenges. High-speed rotation requires extremely strong containment systems. Any imbalance at high RPMs can create safety risks. And energy losses, while lower than older designs, are still present depending on system quality and scale. So at this point, we are left with a very important question. If flywheels are not simple replacements for batteries, why are they being discussed at all in the context of solar energy storage? The answer lies in something very specific. They are not necessarily competing as full replacements. They may instead serve as complementary systems. And this is where things start to become more interesting. Because in real-world engineering design, hybrid energy storage systems are already being explored. Systems where batteries handle long-duration storage, while mechanical systems like flywheels handle rapid charge and discharge cycles. This combination allows each technology to operate in the range where it performs best. And that is where some of the excitement around flywheel technology is actually coming from. Not from replacing batteries completely, but from potentially reducing the stress placed on them, extending their lifespan, and lowering overall system costs over time. However, whether this can truly reach something like a 90% cost reduction depends heavily on scale, implementation quality, and real-world deployment conditions. Because in engineering, theoretical efficiency and practical deployment are often very different things, And this gap between theory and reality is exactly where most of the debate around flywheel energy storage exists today. But to fully understand whether flywheel systems can realistically enter homes and compete with batteries, we need to look at the real-world engineering limitations that rarely make it into viral discussions. Because while the concept sounds simple in theory, the physical execution is extremely demanding. A flywheel system operates at extremely high rotational speeds. In advanced designs, the rotor can spin at tens of thousands of revolutions per minute. At those speeds, even a tiny imbalance can create enormous mechanical stress. That is why safety is one of the biggest engineering challenges. The system must be contained inside a highly reinforced housing, often made with composite materials designed to withstand potential failure scenarios. In many industrial designs, vacuum chambers and magnetic bearings are used not only for efficiency, but also for stability and safety control. But this level of engineering precision comes at a cost. Unlike batteries, which can be mass-produced in relatively standardized formats, flywheel systems require highly specialized manufacturing. Every component must be carefully balanced, tested, and calibrated. This makes large-scale consumer deployment significantly more complex. Another challenge is energy duration. Flywheels are excellent at short-term energy delivery. They can charge and discharge quickly, which makes them ideal for stabilizing power fluctuations. But when it comes to long-duration energy storage, such as storing solar energy overnight or across multiple days, batteries still hold a strong advantage. Because batteries are designed to hold energy statically over time, while flywheels naturally experience gradual energy loss due to residual friction and system inefficiencies. Even in modern vacuum-sealed and magnetically stabilized systems, losses cannot be completely eliminated. So when we hear claims about replacing batteries entirely, engineers are generally very cautious. Instead, the more realistic application being explored is hybrid systems. In this model, solar energy is not stored in a single system, but distributed across multiple technologies. Batteries handle long-term storage. Flywheels handle rapid response and peak load balancing. Together, they create a more efficient and potentially longer-lasting energy ecosystem. This is where some of the excitement comes from in the energy research community, not from a single breakthrough replacement, but from system-level optimization. Now, regarding the claim of reducing solar storage costs by 90%, it is important to understand what that actually refers to. In most technical discussions, such figures are not about the upfront cost of the device alone. Instead, they are based on long-term life cycle modeling. That includes replacement cycles, maintenance costs, efficiency losses, and material degradation over time. If a system can significantly reduce how often expensive components need to be replaced, then over a long enough timeline, the total cost of ownership can decrease substantially. However, this is highly dependent on real-world conditions, manufacturing scale, and technological maturity. At the current stage, flywheel systems are still largely used in industrial and grid-level applications rather than residential homes. But research and development in energy storage is evolving quickly, and what was once considered impractical can become viable as materials improve, costs decrease, and engineering challenges are solved over time. So where does that leave us? It leaves us in a space where the technology is real, the physics is proven, but the large-scale consumer impact is still developing. Flywheel energy storage is not a myth, it is not science fiction, but it is also not yet a direct replacement for home battery systems. Instead, it sits at an interesting intersection of innovation, one that may shape the future of how we think about storing renewable energy. And as solar energy continues to grow globally, technologies like this will likely play a supporting role in building more efficient and resilient energy systems. The real question is not whether flywheels will replace batteries completely, but how they will be integrated into the next generation of hybrid energy storage solutions, and whether that combination can finally solve one of the biggest challenges in renewable energy: efficient, long-lasting, and affordable storage. So now I want to ask you something. Do you think flywheel energy storage is the future of solar systems? Or will batteries continue to dominate for decades to come? Let me know what you think in the comments below. And if you found this breakdown interesting, make sure to subscribe to the channel, turn on the bell icon so you don't miss the next deep dive investigation. Also, drop a comment and tell me what topic you want next. Should we cover new energy technologies, hidden engineering systems, or real-world science breakthroughs that most people don't know about yet? Your suggestion might be the next video. See you in the next investigation.